In this clip, we will consider an ideal gas that is made up of quantum systems. Starting from the grand canonical ensemble, we will derive the Fermi-Dirac and the Bose-Einstein statistics for quantum systems that you might have seen at school, yet certainly you will also in quantum mechanics too. We saw that quantum systems can be easily characterized by their energy eigenstates, epsilon1 to epsilon k. Now we deal in this particular example here with an ideal gas. That means we have n particles. Every particle is identical. That means all those eigenstates are exactly the same. And each particle occupying one of those states. The grand canonical partition function of such a system reads lambda as a function of alpha, beta, and v is equal to sum on all different particle numbers n from 0 to infinity e to the minus alpha n, sum on all states kn e to the power minus beta ekn. Now the trick is to rearrange the sums in this expression. First, let's consider another concept, which is the concept of the occupation number nk. The occupation number nk tells how many particles are in state epsilon 1, how many are in epsilon 2, and so forth. So in this particular example, we have 2 particles in epsilon 2 and 1 particle in epsilon 5. Now in this occupation number view, the total number of particles is just the sum on all states of this occupation nk. And the total energy of the system is again the sum on all states epsilon k times nk. Hence we can rearrange the first expression into an expression where we use our knowledge of the occupation numbers, giving sum on all n, sum of all possible combinations of nks, e to the power minus alpha sum on all k nk minus beta sum on all k epsilon k nk. We have to realize that this tuple nk describes all possible combinations of nks that add up to n. This expression can be further simplified. The sum on all n we actually can take into the different tuples nk, the occupation numbers. Since n runs from 0 to infinity, now the definition of these tuples nk is all combinations of all occupation numbers for all the states. Then the exponential part contains a sum in the exponential which gives the product on the states k e to the minus alpha plus beta epsilon k times nk. Now the sum on all tuples of the product in all states, we actually can rearrange in a way that this will lead to a product on all k's times the sum of all occupation numbers for every state. Hence, we finally obtain that lambda is given by product on all states k, sum on all occupation numbers of that state k, e to the minus alpha plus beta epsilon k times nk. So what we did here is a renumbering of the quantum systems that led to a large simplification of the sums and products that we have to evaluate. So we went from the systems view, where the system is characterized by some energy which depends on the number of particles, into an occupation number view, where we looked into each of those states and asked which occupation number concerns to that particular state, and then the sums on all those occupation numbers can be turned into a product of states of a sum of occupation numbers. So we just derived the partition function of a quantum ideal gas, which is with a logarithm related to the grand canonical potential phi as a function of alpha, beta, and v equal to sum on all states k log sum on all the occupation numbers of that state k e to the minus alpha plus beta epsilon k times nk. So let's further consider the grand canonical potential phi, which is the sum on all states k of the logarithm of the sum on all occupation numbers of state k and k. Now for the occupation numbers, we have to distinguish the kind of particles we are dealing with. If we first consider the bosons, which are integer spin particles, nk can be any number from 0 to infinity. Hence, the sum in the logarithm, sum on all nk, runs from 0 to infinity, e to the power minus alpha plus beta epsilon to the power k. This is geometric sum, which we can solve, yielding 1 divided by 1 minus e to the minus alpha plus beta epsilon k, and the respective thermodynamic potential. For fermions, which are half-integer spin particles, nk can only be 0 or 1. There are not two fermions that can occupy exactly the same state. Hence, the sum only has two parts. Nk is equal to 0 and nk is equal to 1, which you easily can solve, and that yields 1 plus e to the minus alpha plus beta epsilon k, and the respective thermodynamic potential. The thermodynamic potential of a quantum ideal gas, psi of alpha, beta, and v, reads minus or plus sum on all states k log of 1 minus or plus e to the minus alpha plus beta epsilon k, where the minus holds for the bosons and the plus holds for the fermions. From the potential, we now calculate the mean number of particles, mean n, given by minus del phi by del alpha, is equal to sum on all k, 1 divided by e to the power alpha plus beta epsilon k, minus or plus 1. And likewise, the mean energy, given by minus del phi del beta, is equal to sum on all k, epsilon k, divided by e to the power alpha plus beta epsilon k, minus or plus 1. Or the single state occupancies, which only hold for one of those states, k, we obtain the Bose-Einstein statistics, FBE is equal to 1 divided by e to the power alpha plus beta epsilon minus 1, or the Fermi-Dirac statistics for spin half particles, F Fermi-Dirac is equal to 1 divided by e to the power alpha plus beta epsilon plus 1. For high temperatures, the exponential factor will dominate the expression, and we obtain the single state occupancy in the Maxwell-Boltzmann distribution equals to e to the power minus alpha plus beta epsilon. For low temperatures, those distributions are significantly different. Whereas for the Fermi-Dirac statistics at low temperatures, all states below a given temperature are occupied, whereas all the other states are non-occupied. The occupation number for the Bose-Einstein statistics increases with smaller energy. At high temperature, we see that all these distributions get very similar, can be well described by the Maxwell-Boltzmann distribution. From our result, you might expect that bosons and fermions will behave particularly different at low temperatures. This is what you will learn in quantum mechanics too, and also in solid-state physics. Here we will only pick up one particular example and will zoom in on bosonic systems in a further clip.